Welcome back. Let's go straight away to action. We'll talk about today about equilibrium of a rigid body, which I have defined earlier. A rigid body is a bit different from the system of particles that we have been discussing so far, and we have to see as to how this is different. Then first of all we'll discuss the effect of external forces, of course taking that the internal forces, pair of forces F12, F21, they cancel out each other, so we are not interested in that. The internal dynamics, whatever is happening in the body between the constituent atoms, molecules, or say particles, or say the masses that we are concerned. So there are two kinds of equilibria that we may look for. One is the translational equilibrium and the other is rotational equilibrium. And we have to first of all understand, so to build up, the first equation that we have is nothing but the expression of Newton's second law. dP dt, the rate of change of the total momentum of the system, is equal to the force external. So which means we must understand, we should bear in mind that if there is a F external, if there is a force, then there will be a rate of change of the momentum. That means the momentum will change. Okay? So this is about linear momentum. And a similar equation we extract, we obtain with the similarity that there is another equation that we have derived, dL dt, the rate of change of angular momentum, which is equal to torque, tau external, which means, like this case, means that if there is a tau external, then there will be a dL dt, and which means that L will change. So that means the change of L, the angular momentum, due to the torque external. Okay? So this must be borne in mind, it should be clear. And I will explain it further to you. To seek mechanical equilibrium. The mechanical equilibrium therefore means that if there is no rate of change of P or no rate of change of L, that means that the system continues with a constant velocity in the case of translational motion, and it continues with a constant omega, which means that for the rigid body to be in mechanical equilibrium, there should not be any acceleration, and there should also not be any alpha, which is the angular acceleration. Now let me, to make it more vivid, let me write again that this F, whatever, the total sum of all the forces on the system, F1 plus F2 plus Fn, this is equal to sigma Fi, this is equal to 0. The sum of the total forces. And then the same thing I am repeating again, just to build up the subject, that P does not change. So if anything, a vector quantity is not going to change, then all its component along the XYZ directions will also not change. So this is the condition for translation equilibrium, that the total force on the body is equal to 0. In translational equilibrium, the total force acting in the body is equal to 0. Well, similarly, I take this equation, tau 1 plus tau 2 plus tau n is equal to sigma tau I taken over I from 1 to n for all the particles, for all the constituents, for all the masses that are there. And if this is equal to 0, what does that mean? Then the angular momentum of the system does not change. It remains unaltered, it remains sort of conserved. So I can say that the condition for the rotational equilibrium is given by the total torque equal to 0, which is very simple. Now there is a question, and which I am going to address, and the question is, what if the origin about which the torque has been defined, if the origin is changed to another point, what will happen to the torque? Whether it will remain the same or the torque will change with the change of the origin about which the torque has been calculated, estimated, obtained, etc. So the question was, what if the origin about which the torque is taken is changed? So to answer that, I will do a simple exercise for a couple of masses A and B, and we have a pair of forces which annul each out, F acting on B and minus F, which is the parallel one, parallel to that one, is acting on A. Of course, I have taken the origin here and I designate this by R1 and this by R2, the position vectors associated with the points A and B. Okay? So you can see from the head to tail method of addition of vectors that this vector R1 here plus the vector AB here, this is equal to vector R2. This plus this is equal to the vector R2. So, which I am writing over here, and this is the result which I will be using later on. Now, sure that F acts at B and minus F acts at A. So I am emphasizing that. Please look into this and be careful as to what we are going to do. We are going to do a very simple thing. Now, in the course of explaining to you what is a torque, and for the torque, from the bygone days, we use the term the couple also. And when we use the term couple, then the moment of the couple means this F and minus F. The moment of the couple, total moment of the couple will be equal to the sum of the moments of the two forces which constitute the couple, which make the couple. And so I can write for the first one, for this one, I'll write it as R1 cross minus F plus R2 cross F. So if I rearrange the terms, this turns out to be R2 cross F minus vector R1 cross vector F, and if I take F as a common, then I am left with R2 minus R1 cross F. R2 minus R1. So from here you can see that I can write by vector AB, or I can write that R2 minus R1 is equal to vector AB. Very simple, but for beginners you must be careful because I am just using the simple definition of vectors and their summation, subtraction, etc. So there I find, look here, a very interesting result that we arrive at, that this whole thing or the moment of the couple turns out to be equal to vector AB cross F. So if I change my origin to this spot or to this spot, and now there will be a different value of R1 and there will be a different value of R2. Here also, if the origin has been shifted here, then there will be one R1 from here to here and another R2 from here to here. But one thing is not going to change, and that is the vector AB is not going to change. So therefore it shows that the moment of the couple or the torque which we have calculated is independent of the location of O. O may be anywhere. The values of R1 and R2 may change. But for the system of particles that we have taken, in a very simple situation, where there is a couple of forces which are acting on it, they give rise to the moment of the couple, and we sum up the individual couples, and we find that this is independent of the location of the origin. So this is how we address this question. Is interesting, and we should bear in mind that the location of the origin is not important. What is important is the position of two masses A situated at A and at B. So building up from where we left, I am obliged to rewrite the two equations that we have. F1 plus F2 plus Fn is equal to this, and tau1 plus tau2 plus tau1 is equal to this. Okay, with a flaw on my part which I correct. Okay, so the sum of these forces for the translational equilibrium and the sum of all these torques for the case of rotational equilibrium, these two equations have been written, and they do exist, of course. They are in the vector connotation. Now, each of these will have three components: the x component, the y component, and the z component. Here too, and therefore we get a set of 6 equations. First equation, that the x components of the force, they ought to be equal to 0. The summation of the y component similarly, and summation of z component also should be equal to 0. Summation for the torque in the x component, the y component and the z component, all these components, which bear in mind that these are all scalar quantities. So we find that these equations are there. Now we have a set of 6 independent equations, or 6 independent. Why independent? Because these axes are at right angle to each other. They will not have any resolved part. X direction will not have any resolved part in y and z, y direction not in z and x, and z direction not in x and y. So these set of 6 independent equations or conditions have to be satisfied in general for mechanical equilibrium. But normally, suppose we have the forces are coplanar, that is, they are in the same plane. For example, they can be in the xy plane, in the yz plane, in the zx plane, or any other plane, whatever. Then in that case we find that because the conditions reduce to two equations for forces, which is instrumental in understanding the translational equilibrium. And similarly, for the case of the torque, if there are two forces, then there is only one couple that will exist, and that means there is only one torque. So 2 for the forces and 1 for the torque, okay, which becomes essential. The first one of the forces becomes essential for the translational equilibrium, and this becomes instrumental in explaining the rotational equilibrium. Equilibria, translational and rotational, okay, they have been described as absolute equilibria. But next I am going to address to you what is partial equilibrium. Means, in one case we will take two distinct cases. In one case where the translational equilibrium exists but rotational does not exist. In the second case, the rotational equilibrium exists but the translational equilibrium does not exist. Okay, so we are going to learn about the partial equilibrium, but before that I would like to compare the condition of equilibrium of a rigid body with that of particle. The condition of equilibrium of a rigid body with that of a particle. Of course, there shall not be any rotational motion associated with single particle. And because there is no rotational motion, only the condition of translational equilibrium applies to the particle. And the set of forces F1 plus F2 etc. which is equal to 0, we must bear in mind that that is a concurrent set simultaneously taking place over there. Now, to talk about partial equilibrium. Partial equilibrium. We'll talk about the cases where I have a translational equilibrium but the rotational equilibrium is not there, or I have a rotational equilibrium without a translational equilibrium. So I just take a thought experiment, or say even that can be conducted as an experiment, where I have a sturdy rod AB, thin rod of negligible mass. Okay, the rod is straight, it's not flexible. The length of the rod AB is equal to A plus A, that is 2A. On this rod, I apply a couple of forces at the ends A and B. And look here, the two forces are in the same direction. They are in the same direction. We have a fulcrum kind of a thing at the midpoint. So we find that this is a case where the net force on the system is not equal to 0. So there is no question of a translational equilibrium. So look here, torque at A will be equal to the force multiplied by the arc, the arc A, the distance from there. Okay. So I write this equation, tau A is equal to A into F. I'm just taking the magnitude into consideration, although I have shown, and similarly the torque at B is also equal to AF. The two magnitudes are equal, but you can see that the sense of this torque is anti-clockwise here and it is kind of clockwise over here. So the sense is opposite, the magnitude is equal, and this is the case of the partial equilibrium where I don't have a translational equilibrium but rather a rotational equilibrium. So this is the case which I referred to. What I can do now is that while this force is in this direction, I can take the force in this direction, equal but opposite to this force, which I am going to show to you with the help of another drawing. On the contrast, this is the same rod, thin rod, massless, rigid, not flexible, etc., of length 2a, with the central point like in the other example. And now we have two forces, one acting in this direction, magnitude F, and the other minus F, the same magnitude but in the opposite direction. So naturally, the summation of these two forces, which are parallel to each other, of course they are acting at different points in the system that we are considering, that delta F is equal to 0. But if we look at the torque, I'll find that the value of the torque is equal to A multiplied by minus F here, and the sense is kind of anti-clockwise. Okay. And if I look here at B, then again the magnitude of the torque is A multiplied by F, but again you can see that the sense is the same. Okay. Anti-clockwise. So this is the case, this is the situation, and such situations do exist, that we have a case of pure rotation without translation. Of course, as I said, the moments of the forces F and minus F, they are in the same sense. So this is the case of a partial equilibrium, and before I wind up, I can first of all I will give the definition of a couple of forces. It is a pair of equal and opposite forces with different lines of action. Here also, in the other cases, which produce, the pair produces rotation without translation. Equal forces in opposite directions have different lines of action. Couples are also found among humans. Okay. The examples are, for this, applying a couple is a very simple example of opening the lid of a bottle. The lid of a bottle. And what I am applying is, I am applying a pair of forces which go parallel to each other. One here and the other here. Even if I want to close it, then also I have to apply a pair of forces okay, tangential here, and therefore this is the case of application of these principles which we have learned today. The other is that of a compass needle in the field of magnetic field of the earth. Okay, you can look at that, and there are many examples. Probe into them, ponder into them, think into them, all these. So what we have done is a very simple nuance which is called equilibrium of a rigid body, in which I have defined as to what are the various conditions along the x-axis, along the y-axis, along the z-axis, the forces that are there, and the couples that are there. Couples, I mean the torques that are there, and then I have dealt in partial equilibria, where, like in this case, there is pure rotation without translation. In the other case, I have pure translation without rotation, etc., etc. So next we are going to talk about the center of gravity and other nuances associated with the first of all I'll talk to you about the principles of moment. Okay, thereafter we'll extend the results to the calculation of center of gravity, which will turn out in most cases to be the same as the center of mass, if the body under consideration is not very huge in size, so that over the entire volume of the body, entire content of the body, the value of a small g, if it remains the same, then we can calculate the CG and see that the center of gravity is coincident with the center of mass of the system. Thank you very much. We meet shortly.